Hello everyone. This is Yang Su from Zhejiang University. It's my pleasure to be here and present our RAL paper, CARE, Confidence-Rich Autonomous Robot Exploration Using Bayesian Kernel Inference and Optimization. Robot exploration gains its prevalence in planetary, deep-sea, subterranean exploration and field rescue, etc. In these environments, we usually do not have enough prior map information, so we often encounter the problem of a robot deciding where to go next. A popular method to solve this robot exploration problem is to apply information theory, that is, we can choose the travel action that maximizes the gathered information under some constraints such as travel cost and traversability. It's easy to see that it needs the robot to conduct online state estimation and decision-making in exploration. So one of the key requirements for completing information gathering tasks well is to ensure exploration efficiency. This figure shows a typical information-based robot exploration framework, where we can see that, after generating feasible robot actions such as frontiers from the current map, the robot needs to evaluate the information gain of each action to choose the best action to execute. Actually, this evaluation step is quite computationally expensive, since it involves too much forward simulation containing raycasting, mapping, and information gain calculation operations. If the robot stands in a large and complex environment, it may need more candidate actions to keep exploration performance and safety, thereby leading to expensive information evaluation costs. Oh, this is awful. So here, in this paper, we aim to offer two options for accelerating information-based exploration. The first one is called GPBO, a Gaussian process-based Bayesian optimization method for inferring the mutual information of querying actions, where confidence-rich mutual information, shorted as CRMI, is the information metric we use in this paper. However, GP-based inference is more computationally expensive in large scenes. So we propose the second one, BKIO, a more efficient method based on Bayesian kernel inference and Bayesian optimization. We also deploy an upper confidence bound, UCB, comprising predicted CRMI and uncertainties to ensure bounded cumulative regret. Our example code is available on GitHub. Here is a brief framework of our proposed CRMI exploration for efficient inference and optimization, where we apply GP and BKI for CRMI inference, and then use multiple epoch Bayesian optimization to optimize the final suggested action. Finally, the robot executes this best action via local path planning such as DWA*, and conducts SLAM to update the robot pose and environmental map. We use some mathematical expressions to make this clear. GPBO aims to learn a surrogate model for the latent relationship between candidate actions and their MI values. Now we have a training input representing the robot action and a training output representing the MI value. In GPBO, the CRMI of the querying actions can be inferred by the Gaussian process regression. The prediction results include the mean and variance of CRMI. Then we introduce the Bayesian kernel inference technique to infer CRMI without learning a model. It can precisely approximate the surrogate GP model with bounded KL divergence. Assuming the CRMI follows a Gaussian prior, the posterior can be inferred with variance. In particular, we use a Mattern kernel since the unknown environments contain many sudden CRMI transitions caused by terrain and obstacles. Once we get the inferred posterior, we can conduct multiple epoch Bayesian optimization and deploy an information objective function comprising the predicted CRMI values and uncertainties to find the best action for realizing the trade-off between exploration and exploitation. More theoretical details can be referred to in our paper on RAL. Here we come to the experiments section. We first use two synthetic and one dataset maps to demonstrate some primary results. To compare the exploration performance using different methods intuitively, we present the evolution of map entropy and coverage rate of each method in the figures. We also compare the time cost of the entire exploration to show the priority of our proposed methods. This verifies a key conclusion that our proposed BKIO and GPBO methods can improve the time efficiency significantly without losing much exploration performance. We have an exact time complexity analysis of three methods. This comparative result indicates that BKIO outperforms GPBO and naive greedy in time efficiency. The average time cost of each exploration step in the table below also evidence this conclusion. We also study how the UCB function of BO improves the trade-off between exploration and exploitation at each step. As in the top right figure, GPBO and BKIO initially suggested the action towards the B zone. After multiple epoch optimization, the results get closer to the ground truth suggested action. That means the local trade-off between exploration and exploitation in CRMI inference at each step can be achieved using the UCB function. In addition, to balance the time efficiency and exploration performance, we choose 30 epochs in the Bayesian optimization in all simulations and real-world experiments. We deploy our proposed BKIO and GPBO on the Fetch mobile robot using ROS. We conduct experiments in an approximately 25 meter by 35 meter real-world office environment in Level 11, Building 2 of the UTS. The robot explores the environment autonomously and only uses the laser scan data without cameras. Here we use the cartographer as the localization module and CRM as the mapping module in the exploration framework. The robot calls for a self-defined ROS service to evaluate the CRMI of each action generated at the extracted frontiers and then decides where to go at the next step until the exploration ends. The figure below shows the comparative evolution results of map entropy and explored areas using 3 different methods as the travel distance and total exploration time increase. The rapid increase of explored areas in Figure B and Figure D implies our BKIO can drive the robot to explore more unknown areas rapidly, given a limited distance budget, and get an environmental sketch for the subsequent robot application. NG sometimes gets worse because of its myopic planning behavior. Figure D shows that BKIO and GPBO methods outperform the NG in terms of exploration time cost significantly. The mean time costs of each exploration step also evidences the advantage of our proposed methods. Here we have some discussions about our proposed method. Firstly, this paper is not aiming to propose a new exploration framework. The exploration framework we use in this paper stems from the depth-first search, just for running BKIO, GPBO, and NG. Moreover, the information metric here is not limited to CRMI, one can apply our methods to other information metrics for robot exploration. In the conclusion section, we consider that BO-based inference is much better than non-learning ones in efficiency with even better exploration performance sometimes. In addition, UCB ensures the trade-off between exploration and exploitation at each step. Finally, BKIO and GPBO are 2 good options for computationally/energy-limited platforms exploring large unknown scenes. Okay, this all, thank you, and welcome your questions.